Okay, so any question on how to determine graphically the fin efficiency? Okay, now, in additional parameters that can help us to characterize a fin is the fin effectiveness. Okay, you should know the difference between the two. So, the fin efficiency, as we said, is the actual transfer over the maximum possible transfer if the whole temperature of the fin is at T base. While the fin effectiveness is comparing, if you want, the case with fin relative to the case without fin. So the fin effectiveness will give us actually what is the heat convected with fin divided by the case where we don't have a fin. And what is the difference? For example, you know that if I consider a certain surface, okay, the fin will occupy a certain area of the base. So in case the fin is not present, let us consider the following wall, okay? And you have here, this is, if you want, the area where the fin will extend. And the fin is extending in this way, okay? Oh, sorry, like this. The fin is extending in this way, okay? So in case I don't have a fin, this area will be directly exposed to T infinity, okay? So imagine that I don't have the fin. This area will be at T base and is characterized by a certain area. I will call it area of the base. So if I don't have the fin, what will be the heat convected from this area? The heat convected from this area will just be equal to H times area of the base times T base minus T infinity. Okay? And T base minus T infinity is theta 0. So this is theta 0. Okay? Now, what about the actual, what if we have a fin? So if we have a fin, of course, this area will be covered. Yani we cannot consider that this area will do convection. Okay. Well, the area that will do convection is the frontal area, of our fin. Okay. Which is equal to the perimeter of the fin times the length of the fin. Okay. And usually we use the corrected lengths to consider that no heat is convected from this part. Okay. So now we can say that what will be Q with fin? It is, we already have calculated the efficiency. So as I told you, if we have from the graph the efficiency, we multiply the efficiency by the maximum possible transfer, which is the frontal area times H times theta 0. We get the actual heat loss through the fin. And of course, this should be larger than Q without fin. If it's smaller, then no need to put the fin. So the fin effectiveness is larger than 1, okay? Because if it's smaller than 1, this means that the fin is useless. So the fin effectiveness is a parameter that will allow us to see the importance of introducing the fin to enhance the cooling process. So larger the fin effectiveness, the better it is. Okay. And of course, the fin effectiveness will increase with the fin efficiency, will increase with the area, frontal area of the fin, will increase with the convective coefficient. Here, if you want H, in this case, if H is the same, so it will simplify, okay? Theta 0 also will simplify. So we can calculate then, in this case, the fin effectiveness function of the following parameter. Now, in case we have a fin with insulated tip and constant cross section, if we replace in this equation NF by its expression, okay, we got the following form. It's tan hyperbolic ML over radical HA over KP. So how we can get this form from the table? From the table I gave you, we have Q with fin, okay? And we have that Q without fin is HAB theta 0. If we replace, we end up with the following form. And in case the geometry is complex, okay? In case the geometry is complex, we no need to use the table, we use the graphs. So the graphs will give us the expression of the value of the efficiency, and then we just have to replace in this equation to get the fin effectiveness. Okay, now we have studied until now the case of having one fin. But sometimes, and in general, we don't have just one fin, we have several fins. And for this reason, we need to consider the overall picture, okay? So in contrast to the fin efficiency, which will characterize the performance of a single fin, we can define what we call the overall surface efficiency and zero, which characterize an array of fins and the base surface to which they are attached. Representative arrays are shown in the following figure, where S represents the fin pitch. The fin pitch, if you want, is the distance between two consecutive fins. So this is a repetitive pattern, if you want. So each S, I have a new fin. Okay. Now, how we define the overall efficiency in this case? Okay. The overall efficiency of the fin is the actual heat transfer, okay, a Q total, over the maximum possible heat transfer. So again, what do we mean by this? Here, we should pay attention, okay? What is happening is that the total heat transfer that should be considered should take into consideration the fins. You have heat convected by the fins. But also, since you have a space between fins, okay, in this space, you have also convection. So for these areas, you have convection with the outer environment. So Q total here should consider not only the heat lost through fins. So you have, let's say, heat lost by fin 1, fin 2. We have identical fins. Okay, so we can calculate heat lost for one fin and multiply by n, but we should add to this, okay, we should add to this the convected heat through the parts that are not covered by fins, because your base, okay, is formed by areas covered by fins. So these covered areas will not do any heat loss by convection, okay? You just have conduction through these areas and heat will be lost by convection to the outer sides through the fin. While for areas that are not covered by fins, to evaluate heat lost by them, it's very simple. You need to calculate the total area of the base. Here, when they say area base, they mean not covered, okay? So this is the area not covered by fins. Okay. And you know that for this area, how you calculate the heat loss? You say through this area, the heat loss is H times A base times T base minus T infinity. Okay. While for the fins, you have several fins, so each one will do convection. So you should consider that the total area through which we have convection is the area of the base not covered by fins, plus the number of fins times the frontal area of each fin. So this is how you calculate the total area. Now, the maximum possible exchange of heat is if the total area is at which temperature at T base, because delta T will be maximum. So in this case, Q max is H times total area times theta base, while Q total actual is the heat lost through the base that is not covered by fins, plus we should add to it what? Plus Q fins, the heat lost through fins. Okay, and we have seen that if we know the efficiency of each fin, we can calculate this this Q. So we have to multiply. We do n times, okay, Q per fin. And Q per fin can be calculated by knowing the fin efficiency. So if we replace, okay, you say that we have n fin, and for each fin, the heat evacuated is the efficiency of the fin times H times A frontal times theta base, which is the maximum possible exchange for one fin, okay, plus the loss through the non-covered, the area of the base that is not covered by fins, okay? So now, if I want to evaluate Q total, I do the addition of these two terms. And as you can see, I can take in factor, H is common and theta base is common. So we can calculate then in this side, okay, how to calculate the area of base not covered. The area of base that is not covered by fins is actually the total area, okay, of the base. So if you have, for example, if you have here a rectangle, okay, you have thickness times width. You should subtract from it all covered areas by fins. So you should say it's A total of the base minus the number of fins times the area times the value of the area covered by fin. Okay, so if you do this, you will be able to find an expression for Q total. Okay.
Doctor,
Yes.
is it possible to have several fins of different area أو لا دايما بيكونوا same
No,
area؟
no, they will be of same form. If they are of different area, you need to calculate one by one. يعني you cannot come up with a general form.
Yeah, that's what I meant by my
Yes.
question.
So in general, to use these formulas, you need to have same geometry. Okay.
Okay, thank you.
So here, after doing this analysis, we can find a relation between the overall efficiency, okay, and the efficiency of one fin. Okay, so as we said, we write the Q total, we divide it into two parts. We divide it into first, for each fin, what is the heat loss? So this is the heat loss per fin. Okay, we multiply by the number of fins. So this is the total loss through fins. And this is the loss through the area that is not covered by fins. Okay, and if we want to find what is the area not covered by fins, we just have to subtract, okay, the corresponding total area minus the number of fins that we have times their area. Okay, and then we'll get into brackets this term. If you take A total into factor, okay, you will get this term inside. You can say that this can be considered the overall efficiency. The overall efficiency, I will name this term overall efficiency of my fins, okay, which is expressed function of the number of fins, the frontal area of my fins, the total area of my system that will consider everything, okay. يعني the part that the frontal area of fins plus the area that is not covered by fins, okay. And then, of course, from geometry, I can find these parameters. So if I give you geometry, you can calculate all of these parameters, and then you can deduce the overall efficiency function of the fin efficiency. So this formula also will be provided for you in the exam, okay? If not provided, you should just do the analysis, and it's a simple analysis that will allow you to get, no need then if you want to find the overall efficiency. If I don't give you this formula, you can decompose it. You can say I can get Q total by finding the heat loss from fins plus the heat loss from the area of the base not covered by fins. Okay, so please understand the concepts, and in case you have the formula provided, you can directly apply it. Okay. Now, we have already seen that one of the easiest method to deal with conduction, okay, is to consider with conduction and convection in case of steady state without generation, is to consider a thermal circuit analogy. Okay, so we can draw an equivalent thermal resistance system that will allow us to simplify calculations. For example, here, okay, if I have just one fin, what can I say? If I have just one fin, I can say that the conduction flux at the base, okay, will be equal to the convected flux from the fin, okay, if I have an insulated tip. But what if I have several fins? So if I have several fins, it's like the heat will be divided into several parts. And instead of talking about a circuit in series, I will have resistances in parallel. Okay, so the idea here is the following. Whenever you have several fins and you have the base, okay, in general, if you just consider one fin, but you never have just the fin alone, okay, in general, if you have only one fin, you will have it on a base. So you have the base, let's say like this, okay, and you have your fin. So you have here Q total, and Q total here will be divided into two parts. One part that will be evacuated through the fin, that you call, let's say, Q fin. And another part that will be convected through the base, yani Q base. Okay, and since you have the flux will be divided into two parts, then you can consider that you have here a circuit of resistances in parallel. You can consider that I have the temperature at the base here, and at the end I have T infinity. And I can divide my flux. A part will go through fins. So let's say you have N fin, okay? A part of the flux will go through the fin. You can say, if I have N fins, so it's N times Q fin. Okay, and you have from the other side the flux that will go through the base, Q base. And we have developed together for each of these two the expression. And what is Q base? You know that Q base, okay, is equal to the convective coefficient H times area of the base times delta T. And we know that what is the resistance? The resistance at the base is delta T over Q, okay? So which is 1 over H times area base. What I mean by area base is the area that is not covered by fins, okay? And we said how we can calculate this area. Area base can be calculated as the total area of exchange, okay? A total of exchange minus the area of fins, yani N times A frontal of each fin. Okay, so what is the resistance then through the base? The resistance through the base will be just 1 over H times A total minus N times AF. Okay. This is for the resistance through the base. What about the resistance through the fins? Again, we can together find the expression, okay? If you write Q fins total, what is the total heat lost through fins? If you have N fin, okay, you should do N times the efficiency of each fin times H times the frontal area of the fin times theta base. Okay, so if you use the same method, you can say that resistance of fins is equal to 1 over the number of fins. So if it's one fin, you just put n equal 1. If you have several fins, you put n. So n times efficiency of each fin that you get from graph or you get from table, okay, times h times frontal area of the fin. Okay, and now once you have the expression of resistances, you can say since the heat is divided into part evacuated through the base that is not covered by fins and part that is evacuated through fins, I divided into two resistances in parallel. Okay, and you know that if you have two resistances in parallel, how to reduce them to one equivalent resistance. Okay, and your equivalent resistance will be if you want, corresponding to 1 over the overall efficiency of your system, N0, times H times the total area of exchange. So here you can deduce, if you want, from this, you can deduce the expressions that we already found for N0. Okay. Now, what if we have contact resistance? You remember we said whenever we have two surfaces in contact, we have what we call contact resistance between them. Okay. So if they tell you that between the base and the fin we have a contact resistance, then when you draw your thermal circuit, you should add with the fin, and you can consider that Q fin will pass through a resistance of contact first, then through resistance of the fin. So you can put them in series. Okay, if I have n fins, I should put first n times r second, okay, times the area that is covered by the fin at the base. Okay, and then I add in series with it the resistance through fins that I already found before. So what will just change is that you should add here an additional resistance in series because you need to consider contact resistance between the fin and the base. Okay, any question on this?
Doctor,
No,
may you
doctor.
repeat it لأنه I didn't get it كتير كيف
Yeah,
عمل
I will.
الصورة.
Okay, sure. Okay. Look, if I give you which idea, the last one of contact or from the beginning?
If you can from the beginning, it would be good.
Okay, from the beginning. Okay, look. If you have first several fins, okay, and this is your base. The base is the total area here, okay? So your base is divided into two parts. You have parts, these parts not covered by fins, okay? So they can convect heat to the outer environment, while the part covered by fins will transfer heat through the fin, okay? So if you want to calculate the total heat transferred by a fin, you should divide it into two parts. You should say, I should consider the part that is convected out directly through the base, okay? Directly to the outer environment. And you should consider convection from this one plus this one plus all areas not covered, okay? So you can say that I will consider all areas not covered by fins together, and we will call that area AB. AB is the area not covered by fins, okay? And it's equal to this area. How you can calculate it? If you have, for example, a figure, and the total, and if I give you a rectangle, I will give you a profile view, okay? You have a rectangle. You know that you have a length L, a width W, and for example, let's say you have three fins, okay? You have three fins. So 1, 2, 3, for example. Okay. Okay. So you say, what is the area directly exposed to T infinity? This one. Because you don't have a fin here. Okay. You don't have a fin. So how you can calculate this area that is not exposed? You have several methods. First one, if you know the distance between here, if you know this distance D, let's say, okay? So you consider the number of areas that you have, you multiply by D times W. This is a first method. A second method is to say the following. I know the total area of exchange, and A total will consider covered, the non-covered area, okay, AB, plus the number of fins times the frontal area of fin. So if you know what is A total, okay, you can subtract from A total N times AF to get the uncovered area, okay? So it depends on what you know. You can calculate AB. Or you have A total and you have A frontal, you calculate it from A total minus N times A frontal, or you just have the profile. And if I give you the profile of your base, all areas that are not covered by fins, you have several rectangles. Okay, let's say here you have three fins. You have, if you want, a repetitive pattern. Okay, so three fins correspond also to three areas not covered. And in general, it will be a repetitive pattern. And for example, you will have here D over 2. The distance here will be D over 2 from the upper side, okay? And from the lower side also, it will be D over 2. And it will be equivalent to N times, if you have three fins, you have three complete uncovered areas, N times D times W. So this is the total area not covered by fins, okay? Because we consider it's a repetitive pattern. And for each fin, you have corresponding to it an area not covered by fin. And which is, if you want, like this. We consider the pattern. Let me put it in another color for you. You consider this is your repetitive pattern, okay? Yani for each part covered by a fin, you have from this side D over 2 not covered, okay? And from this side D over 2 not covered by fin. So what is the total area not covered by fins? It's the number of fins times D times W in this case, okay? And this area is directly exposed to the atmosphere. So you can consider that for this area, what is Q lost? So Q, if you want base, is equal to the area not covered by fins, I will call it AB, okay, times H times delta T at the base, theta base, okay? Now, if you want to find what is the corresponding resistance, the corresponding resistance, as we know, is delta T over Q. So the resistance at the base is, if you look at the following expression, okay, is 1 over convective coefficient times area of base not covered by fins. Or you calculate it from the figure here, or you can say also that how I can calculate A base not covered, it's A total of heat transfer minus the number of fins times the frontal area of fins. So that's why the resistance at base can be calculated as 1 over H times A total minus NAF. Now, what about fins? We said that the heat will be divided into two parts. A part that will go through uncovered area and a part that will be transferred through fins, okay? So if you have N fins, what will be Q total that will go through fins? It's the number of fins times the heat convected through each fin. How you calculate the heat convected through each fin? You take the efficiency of the fin times the convective coefficient H times the frontal area of the fin times the maximum possible temperature difference, which is theta at base, okay? So here, from this expression, you can come up with what is our fin, resistance of fin. It's delta T. And what is delta T here? It's theta base, okay? It's theta base over Q fin. So if you divide here theta base by Q fin, okay? What will happen is that you will end up with 1 over N times the efficiency of one fin, okay, times the frontal area of a fin times H. So this is how you determine the expression of resistances. And when you want to draw your thermal circuit, since Q is divided into two parts, you have two resistances in parallel. And if you put T base, okay, you have one resistance to fins and one resistance to the area not covered by fins. And then you can replace these two by one equivalent resistance. Now, in case you have thermal contact resistance, if they tell you the surfaces are not perfectly smooth, so whenever you have Q that will go through the fins, it will go through two resistances. First, you will have to go through the resistance of contact, then you should go through the fin. So in this case, you should add to your thermal circuit the contact resistance due to fins. I hope that the idea is clearer now. Josephine,
Yes.
do you still have a question about it?
No, all is clear.
Okay. Any other question on this?
No, doctor.
Okay, next time we'll do together problems to practice on fins, okay? Thank you, guys.
Okay, thank you,
Thank you,
doctor.
doctor.